Hi, good evening, and welcome back to Math Business Applications. I'm Amy Fuchsteiner, your instructor for this course. We are currently working in Unit 7. This is Chapter 11, Compounded Interest and Present Value. Today, we're working on the second section in compound interest, which is Chapter 11, Section 2. We're going to be working on the present value of compounded interest. And as such, we're going to be determining the present value of a future goal. We're going to use, first of all, the present value table, meaning we'll need to be able to find the interest per period, the number of compounding periods in a year, and totaled for the loan. We're going to use those to find a table factor and calculate the present value, and then separate the interest in that account from the compounded amount and from the present value of the account. We want to be able to calculate a new table factor, one beyond the table that you have access to, and we want you to be able to use the present value formula. That means you have to be able to identify the different parts of the formula. You have to be able to use a calculator with a power key to find the present value. And of course, we want you to, again, separate the interest in that account from the principal and the compounded amount. Now, present value is a little bit different. In most situations that you're going to deal with monetarily, you are going to be aware of the goal amount. You will know that you need $30,000 for a home renovation or $4,000 for a vacation. What you might not be aware of is how much money you need today, the present value of that money, so that you have the funds available to you for your future goal. Now, it is worth noting that in today's presentation, what we're talking about is not squirreling money away in a savings account. We're not putting money away every week or every month. We are instead considering it as a lump sum. We want to put away a lump sum of money and then forget about it. So this is more of a set it and forget it than it is a squirrel some money away in little increments over 3 years. All right? Okay, so to calculate that present value, we are going to be using the present value table. You should have access to the present value table. I did put one at the front of this particular week's folder, but the present value table is also table 11-2 in your eText. The present value will be known to you 2 different ways. 3, maybe 3, sometimes 4, 3 for sure. All right, so your table will say on the front of it present value. It will say present value table. All right, in the upper corner here on mine, and I believe in the one in your eText, is the present value formula. Now, initially, we're just going to use the table. It's worth noting that the present value table, all of the numbers are less than 1. All of the numbers on this present value table are less than 1. That's because if I want to have $1 in 5 years, I shouldn't be putting away $1 today. I should be putting away less than $1 because we want our money to grow. So thinking of 5 years from now having 100% of that money, we should be putting away, 75%. 82%. And that percentage is dependent upon the amount of time we have until we want the money and how much the interest rate is per year. So the more time we have and the higher the interest rate, the less money we have to seed the account with, the less money we have to start with. All right? Again, present value. It will say present value or 11-2. All of the numbers in the present value table will be less than 1. Okay. All right. So using the present value table, we have to be able to find the same things as we did for the future value. That is, we have to know the interest rate per period, or the I value. This is your annual or stated rate divided by the number of compounding periods in a single year. The formula, if you would prefer that, once again, is the nominal rate divided by the number of compounding periods in a single year. The number of compounding periods is the number of times we've stopped and added interest into your loan over the course of a year. And the total number of compounding periods is going to be the compounding periods in 1 year times the number of years. So the number of compounding periods in a single year multiplied by the number of years you have until the loan is complete. The present value is what we are finding. In order to find the present value amount, you're going to you're going to find that table factor, and you're going to then multiply it by the future goal. So the present value of an account will be the compounded amount, that's your future goal. Compounded amount is your future goal or the future value, and we're going to multiply that by the present value table factor. All right, come on, baby. Here we go. So here's an example of the present value table. You can see that in the upper left-hand corner, it does say table 11-2. It also says present value table of $1. It is the same. We are going to find the I value in the very first row. Those are going to be a 0.5%, a 1%, 1.5%, and then every percent after that is a whole number. We're going to find the number of periods. This is the total number of periods in the first column. Using that first column and the row, we're going to then find the point of intersection. So we're going to go down the percent column and across the compounding row in order to identify the table factor. And then we're going to take that table factor and multiply the present value or the compounded value, the future value, by that present value table factor. So if we have 3% for 15 periods, we would go across the top row, find 3%, and look down that row. And then in the first row, we'd find 15 periods and follow that across. The intersection of 15 periods and 3% is our table factor. In this case, that's a 0.6418. Notice that that number is less than 1, because if I want to have a specific amount of money at 3% interest for the next 15 periods, whatever those may be, I will need to know that I have 64% of the money to put away today, and then I can set it aside and forget it. Let's try a problem. We have a home renovation planned in 5 years' time. The estimated cost of this renovation is $30,000. The owners are currently able to invest at 4% compounded quarterly. We want to find how much is necessary to put away today in order to reach that $30,000 goal in 5 years, and we want you to be able to calculate how much interest they could earn. So, in order to use the table, we need to find the interest per period and the total number of compounds. So our interest rate per period would be our annual interest rate divided by the number of compounds in a year. This is 4% interest with 4 compounding periods in 1 year. So we'll be looking at the 1% column. For the number of compounds, we have 4 compounds per year for the next, 5 years. So we're going to be doing 4 times 5, and we're going to be looking up 20 periods. Our present value, we want to make sure we're on the present value side, will be for 1% and 20 compounding periods. Looking down the 1% column and across the 20 periods, you should get 0.81954. What this tells us is if I want $30,000 in 5 years and I have 4% interest compounded quarterly, I need to be able to put away 81.954% of that money right now. For the $30,000 I hope to have, that means multiplying 0.81954 times 30,000, giving me $24,586.20. So the thought process here is that, first of all, you have $24,586.20. And if you did, that you could take that money and put it in an account and forget about it. Not touch it. Leave it to earn money for you. for the next 5 years. And if you did that, you would end up with $30,000. So, what's the interest? How did you put in $24,000 and end up with $30,000? The difference is your interest. So the interest earned would be that compounded amount of $30,000 minus the $24,586.20. This leaves you with $5,413.80 as your interest. Make sense? All right. I have in this particular slide just a practice, because I know that this is a fairly straightforward concept, but you need to be able to practice it. So we're looking at a goal amount of $3,500 in this case at a 12% interest rate compounded quarterly for 3.5 years. Using the table, I'm going to find the I value by recognizing that quarterly means I'm doing 4 compounds a year. I'm going to take that 12% interest rate and divide it by 4 to get a 3% interest rate. Total number of compounds would be 4 times the 3.5, or 14. So on the present value table, I'm going to go down to the 3% column, and I'm going to go across 14 periods. And at that intersection, I should find 0.6612. This is the present value table factor. I'm certain that I'm in the ballpark. I mean, maybe I read it wrong, but I'm certain I'm in the ballpark because I know this number should be less than 1. The present value of the money should be less than the future. So 0.66112 seems right. I'm going to multiply that by the goal amount of $3,500, meaning the present value, the money I would need to put away today, would be $2,314.62. The interest earned on this account would be the difference between the present value and the future or goal amount. So $3,500 minus the $2,314.62 for $1,185.38. If you would like to, take a minute and pause this and work through the remaining problems. I'm going to click through them one by one. Here we go. All right, I hope you have the opportunity to do a little bit of practice there. With 11.7, we're going to review how to create a new table factor. The good news is it's the same way as before. So if you were familiar with a little bit earlier in this chapter, I believe it was 11.4, we talked about how to create a new table factor. It is the same process, new table. So if you come across a number of periods that is not on your present value table, what you want to do is decide or determine if the total number of periods is even or odd. And if the total number of periods that you have is even, you simply cut it in half and use half of that number, then find the table factor for that half and multiply it by the rest of them, which should be the other half. Similarly, if your total number of periods is odd, you can use any 2 numbers that add to that odd number. The default in this textbook is that you use 2 numbers that are only 1 apart. So if, for example, you were looking up 35, you could do 20 and 15, but the better option would be to do 17 and 18 because they are only 1 period apart. Once you know those 2 table factors, you simply multiply them together and then round that resulting number to 5 decimal places. And that is your new table factor. As you might imagine, I have a little bit of practice for us. I need to click on this guy because it's just being difficult. All right, so in this world, Grandma and Grandpa would like to pay for college for their grandchild. The estimated cost will be $160,000. If they put that money away at the baby's birth and they have an investment account that pays 6% compounded semi-annually, what's the minimum amount or how much money would they need to put away, assuming that you have 18 years for the money to grow into that 160? Well, we're going to do the same. We're going to do an I and an N, just as we have for every other problem so far. Our interest rate per period would be the 6% divided by the 2 compounding periods in a year, or 3%. Man, that's like the third, fourth, 3%. I did a lot of 3%. All right. Total number of periods would be the number of compounding periods in 1 year. Since it's semi-annually, that's 2. Since it's 18 years, we'll multiply 2 by 18 to get 36 periods. Now, 36 is not on your table, 11-2 table, or the present value table. It only goes up to 25. So we need to figure out a new table factor here. Since this is 36 and it's even, we're going to cut that in half and do 18 and 18. So we're going to look up 3%, same percent, for 18 periods. And then we're going to do 3% at the remaining 18 periods. So when I look that up on the table, I get 0.058739. Notice again, it's less than 1. And I'm going to multiply that by 0.058739. Again, less than 1. This gives me 0.34503. The great news about this is while they need $160,000, they only need to put away 34% of that money. How do I know 34%? I'm simply taking the table factor and converting it to a percent. So they will need to put away 0.34503 by their goal amount, multiplied by their goal amount of $160,000, or $55,204.80. Now, that's still a lot of money. I didn't say it wouldn't be, but it's still a third, essentially, of the amount of money that they'll have in 18 years, which is helpful. All right. So to create a new table factor, again, I have a slide here with some practice. I'll go through the first one and we'll see how it goes from there. So we have a 12% rate compounded quarterly for 10.5 years. Quarterly, again, is 4 times a year, which means our interest rate per period would be 12 divided by 4, and it's another 3%. I might have to do one after this. Total number of compounding periods would be 4 times 10.5, which is 42. Since 42 is not on our table, I'm going to split that into 21 and 21. So I'm going to do 3% at 21 periods times the table factor of 3% at 21 periods, or 0.53755 times a 0.53755, which gives me a brand new table factor of 0.28896. If I had 6% compounded monthly, monthly is 12 times a year. Rate per period would be 6 divided by 12, or 0.5%. Yes, 0.5% is on our table. 12 times 3 is 36 periods. So I'm going to be looking up 1/2 times 18, or I'm sorry, not times, 0.5% for 18 compounding periods, multiplied by 0.5% for 18 compounding periods, or 0.91414 times 0.91414, which is 0.83565. That's my brand new table factor. The next example here is semi-annually and 14%. So my rate per period would be 14 divided by 2, which is 7%. Total number of compounds would be 2 times 21.5, or 43. Now, this is an odd number. So for 43, there are a couple of options. You could do 20 and 23. That would be all right. Any two numbers that add up to 43 will work. You could do 20 and 23, but there's a 3-period gap there. And the book, the procedure according to the book says that you should do the two numbers that are closest together. So I'm going to do 21 and 22 because they're only 1 period apart. So I'm going to look up 7% for 21 periods and 7% for 22 periods. That's a 0.24151 and a 0.22571. This gives me a brand new table factor of 0.05451. I think that's right. Okay. All right. And then the last one is for 1% annually. So we'd have 1% for 39 periods. 39 I'm going to break into 19 and 20, and that should work out just fine. When I look those up, I get a 0.82774 and a 0.81954, which when multiplied together give me a 0.67837. And yes, I know those are behind me, but if you're looking at the original PowerPoint, you should be able to see them just fine. The last section is 11.8, and this is the formula for finding present value. Now, our formula for finding present value is a rearrangement of the compound interest formula, and it says that the present value is equal to the amount, that's your goal amount or compounded amount, divided by 1 plus I wonder, how did that happen? 1 plus I, interest rate per period, to the nth power. 1 plus I to the nth power. Yep, we're going to need to switch that up. Okay, so everything's the same. Your I, or interest rate per period, is the stated interest rate divided by the number of periods. Your N is the total number of compounding periods. That's the compounding periods in 1 year times the number of years. Present value is the amount you're going to have to put in. That's what we're looking for here. And A is the goal amount or the future value. This is the future value or the goal amount. How much will it be worth? All right, so let's try a problem. Here we have Max and Tim, who will have a balloon payment of $42,000 to make on their mortgage in the next 15 years. How much do they need to put away today at 3.3% interest, compounding monthly, in order to make that payment? Now, I know I have to use the formula on this one instead of the tables because my interest rate is not a whole percent. Pretty much every time we've used the table, our interest rates have been whole numbers, 4%, 5%, 7%. The exceptions would be 0.5% and 1.5%. But there's nothing in the table for 3.3. So I'm going to have to use the formula here, and I know it because my interest rate is a decimal. My interest rate per period is going to be the same as it has always been. I is going to equal the annual interest rate divided by the number of compounds per year. The one little sneaky part of this one is because you are putting this into a formula and using your calculator, you must calculate the interest per period as a decimal. So I'm going to take 3.3% and put it in as 0.033, or divide 3.3% by 100, or if you'd rather, move your decimal point 2 places over to the left, however you remember it. So 0.033 divided by 12 is 0.00275. My N, or total number of compounds, is going to be 12 times a year for 15 years. That's 180. That means I can substitute the I of 0.00275 and the N of 180 into my formula, knowing that the goal amount here is $42,000. So the present value is that goal amount divided by 1 plus I to the N, or 42,000 divided by 1 plus 0.00275 to the 180th power. I'm going to do the denominator first, or 1.00275 to the 180th power. So I have 42,000 divided by 1.639384096. Now, if you're calculator savvy, you can do all this in sort of one entry. If you have an older calculator, if you're not calculator savvy, you're going to need to do this piece by piece. If you're doing it piece by piece, please retype as much of that number as you can, because the bank is going to eke every penny out, and so they don't round. And if you just divide by 1.6, you're leaving a whole bunch of money on the table. You really are. Try it. See if there's a difference. And there is. All right, so we're going to take that 42,000 and we're going to divide it by 1.639384096 to get $25,619.37748. rounding everything to the nearest dollar amount, we get $25,619.38. What does this mean? Well, I don't know if you're familiar with a balloon payment in a mortgage, but we'll just give you a little bit of finance information here, just a quick overview. So when you do a mortgage, you generally make regular payments, right? Monthly or whatever. If you choose a mortgage with a balloon payment, basically what you're saying to the bank is, I want you to artificially lower my mortgage payment. So instead of paying $1,200 a month, you're only going to pay $1,000 a month. And those $200 payments that you're missing, you're going to catch up in 15 years with a bulk payment of $42,000. That's essentially what a balloon payment is on a mortgage. They artificially lower your monthly payment, and then at some point you have to catch up. Maybe some of you are like me, and I'm on, for my electrical bill, I'm on the budget. I'm on the budget system, so I give them the same amount every month. And then for me, in October, I have to catch up. So if I'm paying them, say, $96 a month, but by October, that's not enough, I still owe them money because some months I actually owed them more than $96. Then October is my catch-up month, and I make the balloon payment in October, having to pay off anything that was under the rest of the month. That's sort of the idea here with this mortgage and the balloon payment, okay? So they need to put away $25,619.38 today. And if they have that money and they can put it away in an account at 3.3% interest for the next 15 years, then in those 15 years, that money will grow to be the $42,000 that they need to pay it away. You can see that this is savings, right? Because instead of paying $42,000, they're instead paying $25,000, saving themselves almost $20,000 off of their mortgage. So if you have the wherewithal to do it, you're saving yourself money in the long run. It's not always the case. Here we have a problem where Barb and Eddie are planning a road trip on Route 66 in the next 3 years. This is actually something people I know have done, that for their 66th birthday, they got a bunch of people together and traveled Route 66. It's super cute. All right. They estimate that $8,000 should cover their expenses. That's the rental, the hotels, the whole thing. How much should they place in an account earning 4.2% interest, compounding quarterly for the next 3 years in order to have that $8,000? So we're going to do the same sort of process here. We're going to find the interest rate per period. Since it's a 4.2%, I know I can't use the table, so I'm going to do my interest rate as a decimal, 0.042, dividing by 4, because it's compounding quarterly, and I'm going to get 0.0105. Total number of compounding periods is 4 times a year for the next 3 years, so 12 compounding periods. My goal amount, or Barb and Eddie's goal amount, is $8,000. So I'm going to substitute these values into the formula, the goal amount being $8,000, my interest rate, or I, per period being 0.0105, and my total number of compounds is 12. So this becomes 8,000 divided by 1.0105 to the 12th power, or 8,000 divided by 1.133537297. This turns out to be $7,057.55. So in this particular problem, the amount of interest that they're earning is not quite $1,000. So if they want $8,000 in 3 years, they have to be able to put $7,000 and change aside today. That doesn't seem like as big a savings. Like over the course of a year, I could probably save $1,000 maybe, or find a better use for it. But you can see it's still a savings. It's just not always as impactful. In order to be impactful, your savings needs time and a higher interest rate. So the difference between 3 years and 15 years is quite a bit of interest. As I have with the last 2 sections, I also have a slide here with just some calculator practice. The formula, again, is present value is equal to A divided by 1 plus I to the N. This finds you the present value or the principal that you should put down. I'm going to click through this guy, maybe do a couple of examples. If you want to have $6,000 and you have 3 years and a 9% interest rate compounded monthly, keeping in mind that monthly means you have 12 compounding periods, we're going to take the interest rate as a decimal, 0.09, divide that by 12 to get 0.0075. This is our interest rate per period. Total number of periods would be 3 years times 12 times a year, or 36. The formula would be the goal amount or the compounded amount or the future value divided by 1 plus I to the n, or 6,000 divided by 1 plus 0.0075 to the 36th power. If you do this, you should get $4,584.89. If you would like to have $50,000 and you have 25 years, okay, it's a lot of time. So my present value should be relatively small compared to the $50,000, because the more time you have, the further away from your goal amount you can go. All right, we've got 5.2% compounding quarterly. Quarterly is 4 times a year. So I'm going to take 0.052, because I'm putting it into a formula, divided by 4 to get 0.013. Total number of compounds is 4 times 25, or 100. Present value formula is the goal amount divided by 1 plus I, interest per period, to the nth power, or 50,000 divided by 1 plus 0.013, to the 100th power, and I get $13,741.23. Compared to the $50,000, this is very little, right? $50,000 versus 13 or 14 almost. But you got 25 years to grow. 25 years for the money to grow. And when you have a lot of time, you can start with a smaller amount of money. All right. These last 3 problems here, I'm just going to click through this next one. And then I'm going to make a point on this one that's $500,000. Here we have I would be 0.03 divided by 365, or 0.0000, it's 4 of them, right? 82192. This is a very awkward number. Sometimes when these numbers don't work out very well, when you get a lot of zeros in front of it, or when it doesn't divide out and terminate, it's actually better to type it into your calculator just as 0.03 divided by 365. That would be an absolutely fine way to type it into your calculator, and that would not cause an issue at all. All right. So I'm going to leave you here with this last one. I am, of course, blocking the answer, but you should get $22,902.74. That's all there is for section 11.2. It's a lot of rehashing. It's just being able to know the difference between present value and future value. Unfortunately, the processes stay very much the same. So at this point, do you feel like you can determine the present value of a future goal? Can you do so using the present value table? Are you fairly confident in finding the interest rate per period, the total number of compounding periods, and calculating present value? Not only that, but are you able to identify the interest and the principal and the compounded amount? Can you calculate a table factor beyond what's given to you in the table? And are you comfortable using the present value formula? That means, are you able to identify the parts, and can you use a calculator itself to determine what that present value would be? And not only that, but can you once again separate the compounded amount, future value, the goal amount, all 3 of those are the same thing, from the interest and the principal? There is extra practice for this section in your eText at the end of Chapter 11, Section 2. The review exercises are, I believe, 1 through 29. If you have a physical copy of the textbook, you can find this information on pages 358 to 360. I'm sorry, it's not information. You can find these practice problems on pages 358 to 360. There is a graded assignment available on WebAssign. It is creatively labeled Chapter 11, Section 2. If you have any questions or concerns, please don't hesitate to reach out to myself, to your embedded math support, to the Math Center, or to a tutor that you may have available to you. We want to see you succeed. We are all here to help. Thank you.